So the other day in class we talked about differentiability. Let's take some time to go over some of what we said. So first, we recalled that a differentiable function of a single variable enjoys a number of important properties. 1. The graph of y equals f of x has a non-vertical tangent line at the point x0, f of x0. 2. The function f may be closely approximated by a linear function near x0. And 3. The function is continuous at x0. We want to extend the notion of differentiability to functions of two or more variables so that the analogs of these properties hold. Specifically, if f of xy is a function of two variables that is differentiable at the point x0, y0, we want it to be the case that 1. The surface z equals f of xy has a non-vertical tangent plane at the point x0, y0, f of x0, y0. 2. The values of f near x0, y0 can be very closely approximated by the values of a linear function. And 3. The function f is continuous at x0, y0. One might think that a function f of two variables should be differentiable at a point if all the first partial derivatives of the function exist at that point. But this condition isn't strong enough to guarantee that the aforementioned properties hold. For example, consider this function. F of xy equals the negative of xy over x squared plus y squared, where xy is not 0, 0, and define f of xy to be 0 when xy is 0, 0. I'll leave it to you to see that both first-order partials exist for the function at 0, 0, but that it fails to be continuous there. To see what else we need in our definition of differentiability for a function of two or more variables, let's take a closer look at the second consequence of differentiability from earlier, namely that the values of f near a point can be approximated by a linear function. Let's begin by looking at the graph of a function of a single variable. And let's identify 2 points on the graph, one at x0 and another at a certain distance away, say delta x units away. The corresponding points on the graph are x0, f of x0, and x0 plus delta x, f of x0 plus delta x. We can consider the change in the x values in going from this lower point on the graph to this higher point, and we can consider the change in y values as well. The change in x values is represented by this horizontal segment. It, of course, is delta x. And the change in y values is represented by this vertical segment. It will be denoted by delta f, where delta f is f of x0 plus delta x minus f of x0. Now let's consider the tangent line to the graph at the point x0, f of x0. And here we see the tangent line. And the slope of that tangent line, of course, is f prime of x0. Alternatively, the slope can be obtained by looking at the change in y's over the change in x's, given that we know 2 points on the line. Well, here's 1 point on our line, x0, f of x0, and a second point on our line can be this point up here, just above the given point on the graph of our function. So given these 2 points, we need the change in the x values between them, which of course is delta x, and we also need the change in the y values between those 2 points, which we can represent by this line segment shown in red. We wouldn't refer to this distance as delta f. Delta f, remember, referred to this vertical distance. So to refer to this full vertical distance shown in red, we need something else. We'll refer to it as df. Consequently, the slope can be written as df over delta x. And instead of using delta x, let's use dx just for consistency's sake. As such, the slope here is df over dx. From these two, it then follows that f prime of x naught is equal to df over dx, or that df is equal to f prime of x naught times dx. Now note again that df and delta f are different. df represents this vertical distance shown in red, the vertical distance between these 2 points on the tangent line, whereas delta f refers to this vertical distance shown here, which is the vertical distance between these 2 points on the curve. Nevertheless, delta f can be approximated by df, provided that this horizontal distance is small. So delta f is approximated by df, provided that the horizontal distance here is small. But from this it follows that delta f is approximately f prime of x naught times dx. dx, however, is the same as delta x. So delta f is approximately f prime of x naught times delta x. Again, this is an approximation, and the error in the approximation is simply the difference between delta f and f prime of x naught times delta x. If delta x is close to 0, the error in this approximation will have a magnitude that is much smaller than that of delta x. To see this, let's consider the limit as delta x tends to 0 of delta f minus f prime of x naught times delta x over delta x. But this is the same as the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught minus f prime of x naught delta x all over delta x. Notice that this difference right here is simply delta f. But this then can be decomposed. We can write the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught over delta x minus f prime of x naught delta x over delta x. Note that we're taking the limit of this entire expression. Moreover, note that the delta x's here cancel out. As such, this term no longer involves delta x, and as such can be brought outside of the limit. We can therefore rewrite this as the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught over delta x minus f prime of x naught. But note that this limit is the definition of f prime of x naught. And so we have f prime of x naught minus itself, which of course is equal to 0. So what this tells us is that the magnitude in the error of the approximation, delta f minus f prime of x naught delta x, is very small in comparison to that of delta x. And it's the extension of this idea that we need as the extra ingredient for the definition of differentiability for multivariable functions. So to this end, for a function of two variables, f of x, y, let's take delta f to be the difference between f of x naught plus delta x, comma y naught plus delta y, minus f of x naught, y naught. And by analogy to the one variable case, let's make this approximation. Delta f is approximately equal to the partial of f with respect to x at x naught, y naught, delta x, plus the partial of f with respect to y at x naught, y naught times delta y. We define the error in the approximation to be delta f minus the partial of f with respect to x at x naught, y naught times delta x minus the partial of f with respect to y at x naught, y naught times delta y. And we want the magnitude of the error in this approximation to be much smaller than the distance between x naught, y naught and x naught plus delta x comma y naught plus delta y. We want this limit to be 0. This then tells us that the magnitude of the error in the approximation is much smaller than that of the distance between the 2 points. This then gives us that extra ingredient we need in the definition of differentiability. We say that a function f of 2 variables is differentiable at x naught, y naught, provided that 1. The partial of f with respect to x at x naught, y naught, and the partial of f with respect to y at x naught, y naught both exist, and that the limit as delta x, delta y approaches 0, 0 of delta f minus the partial of f with respect to x at x naught, y naught times delta x minus the partial of f with respect to y of x naught, y naught times delta y over the square root of delta x squared plus delta y squared equals 0. Using this definition, we can prove the following result. If a function is differentiable at a point, then it's continuous at that point.